Okay, good morning, everyone. How did your homework go? Do you have any questions before we start? As usual, please put your questions on chat. Okay. So we 9 and 30. So we look at those. Number 9. Let's look at number 9. Okay, so we're gonna first look at number 9. So I will need the book and to talk a little bit about it. Okay. So the question is, approximate the area of the region bounded by the graph and the x-axis by dividing the interval 1, 7 into 6 subintervals. Okay, so let's look at the picture right here. That's my graph, and the question is, we have to approximate the area. Now, of course, that's a function that's curving, so we need to approximate the area using 6 subdivision and left and right Riemann sum, which obtain 2 different approximations. So the problem is exactly like we did in class, but here, instead of having the values obtained by a formula, is the graph which gives us the value. So my interval is 1, 7. So that's my interval, 1, 7. And the number of subdivision equal to 6. So the delta x, it means the length of every subdivision is, the length of every subinterval is 7 minus 1 over 6, which is, I think, equal to 1. Okay, so I will do the left sum, and then the right sum will be exactly the same. So we have L6, it means the left sum. And what it is? And every interval is the output at the left point times the area. Okay, so we can like have a little table to make this problem a bit easier. We can just help ourselves with a little table to give me the value at the interval. So what is at 1, 2, 3, 4, 5, 6, 7, just to make it a little bit easier for us. So at f of 1, according to the picture, it's a 10. F of 2, it's a 9. F of 3, it's a 7. F of 4 is a 5. F of 5 is a 2. F of 6 is a 1. And F of 7 is a 0. Okay, these are the value picked. So what is the left sum? It's the value of function at 1 times delta x. So which is give me the area of this rectangle. So it's exactly what we did, just times 1, that's the delta x, plus f at 2 times 1, plus f of 3 times 1. And every time I'm getting an area. Every time I'm getting an area. So I'm getting an area. I'm getting an area. That's really what we're doing. Plus f of 4 times 1, plus f of 5 times 1, plus f of 6 times 1. And since it's a left sum, that will be my last rectangle. So that's really the rectangle we are using to approximate this area. And now it's just a matter of adding. And then we get exactly the number. So it's 10 plus 9 plus 7. Delta x is 1, so I'm not changing. Plus 5 plus 2 and plus 1. So the left sum, so that's an approximation of the area, of course. So that's going to give me 3, 8, 15, 15 and 9. That's going to be 24, which will give me 34. Okay, so that's the left sum. Now the right sum we take the value at the right endpoint. So this is not the picture anymore. My first rectangle is f of 2. So that will be my first rectangle. My second rectangle will be this one, and then so on and so forth. My third rectangle, my fourth rectangle, my fifth rectangle, and my last rectangle, because f of 7 is 7, is going to be just a straight line. So the picture changed. So r of 6 is going to be the value at the right point plus f of 3, f of 4, plus f of 5. I'm not ignoring delta x, but delta x is 1, plus f of 6 times 1 plus f of 7 times 1. So this is nothing more than it's a 9 times 1 plus 7 plus 5 plus 2 plus 1 plus 0. And then we do the math, so we're going to have 25. Okay. So that's the left, and we know that the area is neither the left nor the right. So one possibility to a good estimate for the area, if you want, you can almost, if you want, you can average them, because we know that, we know that it's either one of them. So you can either take more subdivisions, which give you a better approximation, or you say, you know, it should be the average between them, if you want. So it means it should be the average between them, which is going to give me 59 over 2. So 59 over 2, which is 29.5. So that would be a good estimate of the area, averaging those two. Okay. So it's the same approach, but instead of giving the function a formula for the output, they're just giving us a graph. Okay, now we look at number 30. And let's see, do I need the book? Number, sorry. What's number, where is 30? Ah, 30 is right here. So 30 is exactly like we've been doing. So we will look quickly at it and then we proceed. So number 30. So number 30 is just a function f of x equal to x squared on the interval 1, 1, 6, and the number of subdivision is equal to 5. Okay, so the picture first, and then we proceed. So the picture. Okay, 2x squared, that's a parabola. Both parabolas. But we're only interested on 1, 6. That's 1. That's 6. So that's my interval that I'm interested in. I'm interested basically in this area up to here. And we have to evaluate it. Now, they ask several questions. Sketch the graph with it. Calculate delta x and the grid point. So delta x here is, of course, I don't know why they give us such an easy delta x. It's the length divided by 5. So that's a 1. And then the grid point. What I mean by the grid point, it means when you subdivide into pieces, 1, 1, 2, 3, 1, 2, 3, 4, 5. The grid point, it means they want those points. So here, because delta x is 1, so that should be a 2, a 3, a 4, and a 5. These are the grid points. And now we just have to evaluate them. So what do they want? Illustrate the left sum and the right sum, then determine which one underestimate and which one overestimate. So first let us focus on the left. And the right is the same. I will not do the right, I will do the left. So what is illustrate? It means we take the value of the function at the left hand point, we multiply it by delta x. That's the illustration. Plus the value at the left point and times delta x. The value at the left point, delta x. The value at the left point, delta x. The value at the left point and delta x. So these are my rectangle. That's the illustration. This one, this one, this one, and that one. So these are my illustration of the rectangle. And now what's the left sum? It's the sum of the areas, basically. So the left sum, L5, because I have 5 subdivision, is f of 1, that's the area, plus f of 2, that's that area, f of 3 is this area, f of 4 plus f of 5. And we stop, because my last rectangle is obtained, the height of my last rectangle is f of 1. So always the picture is the height, the width, height, width, height, width, height, width, and height times the width. And now we just compute. What is f of 1? My output here is, if x is the input, my output is 2x squared. So this will give me 2 times 1 square times the delta x, which is 1. And this is 2 times 2 squared. That's the height times the width. The height times the width. The height times the width, and then the height times the width. And the rest is, you basically take our calculator and compute it, nothing more than that. And we get a certain answer, which is nothing more than, you just compute. So that's a 2 plus 8 plus 18 plus 32 plus 50. So we just add those numbers. And the question is, does the 3-month sum underestimate or overestimate the area? So does it underestimate? Is it less than the area, actual area, or more than the actual area? So very quickly, compare to the actual area under the graph. Okay, is this underestimate or overestimate? Is it less or more? Quickly, just by looking at the picture, and definitely it's less than the actual area. Okay. Absolutely, yes. Now the right is the same. I will not do the right because the right is verbatim the same. And the only difference is that I start at 2. So in the right, I would draw on the pane, I take f of 2 times delta x. So this would be my rectangle. F of 3 times delta x. That would be my rectangle. F of 4 times delta x. F of 5 times delta x. But I have also to take f of 6 times delta x. And those will definitely overestimate the area. Right? Okay. And then you can do the same thing using midpoint sum. And the midpoint sum, it will be, you take the height, the value right at the midpoint. As simple as that. That's the idea. All right. Today we're going to keep along the same line, but we're going to make a certain change, which is an important change. Today we are going to define what we're going to call left 3-month sum, right 3-month sum, and the idea of definite integral by the same definition. I mean, we're going to use the same definition, but what we're going to change is we're going to allow the function itself take positive and negative value. Because watch carefully here. The function has to be positive, because otherwise, if the function is negative, the height will be a negative number. So it means if the function go like that, the height will be negative. So the height times the width will not be an area anymore because the height is negative. So in this problem, for L6 to represent the sum of the area of the rectangle, we have to have a positive function. Now I'm going to remove this condition, and we're going to see what happens if we don't assume function positive. Those sums, this exact same sum, what do they represent? Okay. So this will move me to section 5.2 and definite integral. So, okay. Definite integral. Definite integral. So we saw what's called indefinite integral, which is nothing more than the antiderivative. Now we're going to define the idea of definite integral. So first, Riemann sum. Again, the same word, Riemann sum with n subdivision. I'm gonna repeat basically the same definition I did last time. All right. Now let f be a function. Let f be a function. On AB, defined on an interval AB. Okay. The only difference here, f is not necessarily positive. And that's going to be the method. F is not necessarily positive. In other words, f takes positive and negative value. It means f takes positive and negative value. Positive and negative, not necessarily positive. Okay, so that's my function f in my scenario. So this is my f. This is point A, this is a point B, and my f take everything. So this is my function f. That's my function f. Okay. Now we're going to define what we call left Riemann sum, midpoint sum, and right Riemann sum. Verbatim the same. It's the interpretation that was gonna change this time. So we're gonna divide the interval AB into n equal pieces into n equal subinterval, like we did. So equal subinterval. Okay, and delta x is the length of each one of them. So my delta x is from here to here. That's my delta x. That's my delta x. So my delta x is b minus a over n. It's the length of those little intervals. Okay, and the grid point, we're gonna call them. Everything is verbatim the same. So I'm gonna really almost repeat myself. So the change will be in the interpretation, x0, x1. And then we're going to define the left Riemann sum as follows. Left Riemann sum to be exactly the same. And I'm going to rewrite it in sigma notation so we get used to it. So it's the value at at x0 times delta x plus the value at x1 delta x plus, I keep going. My last one is going to be the value at this point. This is xn minus 1 times delta x. So our left sum is sigma. I'm adding stuff. What's changing is the subscript 1. So this one, I put it f of xi times the delta x. And my I goes from 0 to n minus 1. So no change in the definition, the change in the interpretation of the sum. The right Riemann sum is the same thing as before, but I start at x1 all the way to xn, and in sigma notation, it's the sum of the xi times the delta x. My I goes from 1 all the way to n. And this delta x here is the b minus a over n. That's really what my delta x is. My delta x here is the b minus a over n. And finally, the midpoint sum. The midpoint sum is again defined verbatim the same. So if you guys are writing down, I keep this here. And make sure you know how to write this sum. Make sure you know how to write the sum. It's really, really crucial to know it. And the midpoint sum is the same. I take sigma f at x star I delta x, I equal 1 to n, where the xi star is the midpoint. Is the midpoint. of the interval xi minus 1 xi. So everything is verbatim the same. So now the question is, what does the left sum represent? And the right sum and the midpoint sum when I'm assuming this function takes positive and negative. So the first part is mainly to remind you the definition, nothing changed. Now we're gonna interpret it. So I'm gonna take the following function. So let's see how to interpret the sum. Okay, and if you guys are writing, you can say, so basically the example is how to interpret at least one of them, because if I interpret the left sum, the right sum, the midpoint sum will be the same idea. So let's see how to interpret left sum. Okay, so I'm going to take the function f of x to be 1 minus x squared. And on the interval, a b equal 0, 3. Okay. And my first question is, so this is my function here. That's my function. 1 minus x squared. So 1 minus x squared, that's a parabola going down and then shifted by 1 unit. So this is a 1. So I'm graphing the function first. And it is a parabola and goes like this. So that's really my function. And this is my 3. That's the interval 3. Now what's this point here? This is curving. This is not a straight line. It looks like a straight line. It's not. So this is f of x equal 1 minus x squared. So this point here is when the function takes the value 0. So this the point here is 1. Okay, so that's really my function. That's the function here. Now, the first question is find the left sum. So I'm going to keep this picture here. I'm going to go back to it. So the first question is find the left sum. Okay, let's find it here. Not interpret, find L5. Find left Riemann sum. Riemann sum with, let us say, 6 subdivisions. Okay, so the first question is just find the left Riemann sum. The second question is to interpret that. So here the delta x is, since I want 6 subdivision, it means I take the interval between 0 and 3. That's the length of it. And I'm going to divide it into 6 pieces. It means each one is a half. So I go here and I divide it. So that's a half, 1, and the 2, and the half, and the half. So this is my subdivision. Okay. So this is a half, 1, 3 half, 2, 5 halves, and 1. And what is the Riemann sum? L6. Right. It's f of 0 times a half plus f of 1 times a half, f of 1 half or 3 half times a half. So this time I'm just using the definition. I'm not interpreting, as you realize. F of 2 times a half plus f of 5 halves times a half. So that's really the definition. And we compute this. So you know what, I compute this. So that will be 1 minus 0 squared times a half. That will be 1 minus 1 times a half. And that would be 1 minus 3 half square times a half, 1 minus 2 square times a half, and 1 minus 5 half square times a half. I'm just computing. Now I pick up my calculator and I add those numbers and I get a minus sign. I get a minus 3.875. Okay, so that's nothing but a number, which is minus 3.875. Now I'm going to go back to the picture. And and we want to interpret this. What does this number represent in the picture? What does this left Riemann sum represent? Okay, let me go back and work with it. F of 0 times a half. I'm going to take, this is 0, and that's f of 0 is from here to here. That's f of 0 times a half. So I'm going to draw those rectangles. F of 1/2 times delta x, I'm going to draw this. So that's from here to here. That's f of 1. That's f of 1/2. Okay. Then I have f of 1 times delta x. F of 1 is 0. Then I have f of 3/2 times delta x. Then I have f of 2. This is 2, and this is f of 2 times a half, and then f at 5/2 times a half. Okay, so this is the sum. Now let us interpret every term of this sum. F of 0 times a half. What does it represent? This is f of 0. F of 0 times a half represents the area of this region. We're going to call it D1, the area of D1. F of 1 times a half. What does it represent? Sorry, that should not be f of 1. Why don't you guys correct me? I'm missing f of 1/2 times a half. So I'm missing a term in here. I'm missing a term. So f of 1/2 times a half, if I call this region D2, is going to represent the area of D2. Now, f of 1 is 0. Let's not worry about it. The question is f of 3/2. What is f of 3/2 times a half? What does it represent? F at 3/2 is a negative number. And I'm going to multiply it by a half. What's this going to represent graphically? I want you to think about it a little bit. Okay? So, you guys think a little bit. Okay, I want you to think, what does f of 3/2 represent here? Anybody? Okay. F of 0, area of D1. F of 1/2, area of D2. Now, this happened to be a 0. What is f of 3/2? The value of f at 3/2 is a negative number. Okay, so f at 3/2 is negative because f of 3/2 is 1 minus 3/2 squared. So it means 1 minus 9/4. It means minus 5/4. So this value here is minus 5/4. So when I take f at 3/2, it means minus 5/4. And I multiply it by delta x. So when I'm taking minus 5/4 and I'm multiplying by a half, will I get the area of this region? Yes or no? I'm going to call this region D3. Will I get the area of the region? Yes or no? What's the relationship? I ask you the question again. When I take f of 3/2 times a half, what am I going to get? F at 3/2 is a negative number. When I take minus 5/4, because that's how times a half, is this going to give me the area of D3? Yes or no?
No.
No, because the area cannot be negative, right? That's as simple as that. But what does it actually gives me? It actually gives me minus the area of D2. Doesn't give me the area. It gives me minus the area because the length from here to here is actually 5, 4 because that's the value of the function. This is 5, 4. When I multiply it by a half, I get the area. But since I'm taking the value of the function, it means I'm taking minus 5 over 4. So this quantity here is going to give me minus the area of D2. So when my function is taking negative value, when I take the value of the function times the delta x, I don't get quite the area. I get minus the area of this rectangle. So in the picture here, this term where f is negative, this is minus the area of, I want to call this D4, minus the area of D4. That's what's happening here. Plus, this is my 2. The value of the function at 2 is negative. So here my function is negative. So I'm gonna call this region D5. So when I'm gonna take f of 2 times the delta x, I will not get the area of D5. I'm gonna get here again minus the area of D5. So it's not the area, it's minus the area because the function here is negative. So when the function is negative, when the function takes negative, f at a point times the delta x represent minus the area of the rectangle, not plus the area. So now if I proceed here, at 5/2, I call this D6. Again, my function is taking a negative value. So this term here is again not the area, is minus the area of D6. So let us a little bit read and interpret. So what this left sum represent? Area of D1 plus the area of D2 minus the area of D4 minus the area of D5 minus the area of D6. So it's basically where the function is positive is the sum of the area of the rectangle. When I start taking negative, I start taking negative this area, minus this area, minus this area. So that's why when I evaluated the sum, I'm getting a negative number because now I'm taking positive areas minus the area below the x-axis. So if I rewrite this, so this is my L6 now. So it means it's going to be equal to, I'm going to rewrite it like that. It's area of D1 plus area of D2. And this is D1 and D2. I cannot lose track of my picture now. Minus, I'm going to factor out this minus here, minus area of D4, I'm factoring it out, plus area of D5 plus the area of D6. So it means the left sum is going to represent the area of D1 plus the area of D2. It means sum of the areas of the rectangle, the sum of the areas of the rectangle that are above the x-axis, above the x-axis, minus sum of the area of the rectangle that they are below, of the rectangles that are below the x-axis. Below the x. So the geometry now, definitely the interpretation of the left Riemann sum is definitely different. The same will be for the right Riemann sum and the midpoint sum. It's really the same, absolutely same principle. So let us summarize a little bit. When the function takes positive and negative value, where the place where the function is positive, then the left Riemann sum, the term of the Riemann sum that correspond to when the function is positive, their contribution to the picture is the sum of the area of the rectangle. When the function takes negative value, the contribution of those terms is by giving us minus the area of those rectangles. So this is what the left sum really represents. Now, of course, if I take more subdivision, it's the same picture. More subdivision, I will have exactly the same picture. So this is the left Riemann sum. Now we're going to define, so the same way I did L6, I can start doing longer subdivision, L12, L100, and so on and so forth. So as I take more and more subdivision, I'm going to get, actually intuitive, what's going to happen is the following. I'm going to get the area, I'm going to cover more of the area of the part above the x-axis and more of the area below the x-axis. So intuitively, what I'm going to get when I take more subdivision is the area of the region above the x-axis minus the area of the region below the x-axis. So that's what's going to happen eventually when I take larger and larger number of subdivisions. Now I'm going to define the notion of definite integral. So after this interpretation, we're ready for the most important definition in this chapter, definition of definite integral. So what is the definite integral? It's nothing more than what happened to those sums when n becomes larger and larger and larger. So it's nothing more than what happened to left sum, right sum, midpoint sum, when the number of subdivision increase. So definite integral. Okay. So let f be a function, not necessarily positive. Definite integral. Okay. Let f be a function defined on the interval AB. And f not necessarily positive. And that's crucial now. I'm not assuming that my function is positive. Then the definite integral. The definite integral of f on the interval AB, which is denoted by. Now I will write the notation and then I'll explain verbatim. That's the notation of definite integral. That's like the integral sign before. At the lower here, we put A. At the upper here, we put B. And inside here, we write f of x dx. So the definite integral denoted by this is defined by. Okay, so what is the definition of the definite integral? The definite integral is nothing more than what happened to the left sum or the right sum or the midpoint sum when the number of subdivision goes to infinity, becomes very large. So that's exactly what I'm going to write. It's the left sum. So the left sum, f of xi delta x, I equal 0 to n minus 1. So this is the left Riemann sum. And what happened to those when n, the number of subdivision, goes to infinity? N is the number of subdivision. N is the number of subdivision. It means you compute the left sum for 100 subdivision, 200 subdivision, I don't know, 1,000 subdivision, and we ask yourself, what happened to those sums when the number of subdivision goes to infinity, becomes very large? The number you get to is what we call the definite integral. Now I put the Riemann sum, the left. We could have done it for the right or the midpoint. They all will give me exactly the same answer, which is, of course, there is a proof for that, but we accept it. So, or I can say the limit of the right Riemann sum, and the only difference, so that's n, the number of subdivision, that's what goes to infinity. And here is the xi delta x. But here my I start from 1 because that's the right sum. The right sum. or we can use the midpoint sum. All of them will give me exactly the same answer, or the midpoint sum. So for the midpoint, that's I call this x star delta x. N, the number of subdivision goes to infinity, 1 to n. And those are the midpoint. Okay, so that's what the definite integral is. Nothing more, I mean, it's not nothing more, it's those left sums when the number of subdivision, n is the number of subdivision goes to infinity. Now, what is the notation of definite integral coming from? So a little bit of the terminology and terminology. Okay, first, where is this notation coming from? What does it reflect? This sign, this one is the letter S elongated, if you want. What S represent is sum. S stands for sum. So this sign here, so where is this notation coming from? That's what I'm trying to explain. This sign, this one, is represent that we are adding things. That's what it really intuitively represents. It means we're adding. It's a sum. It's the sum of what? It's the sum of quantity of the form f of xi delta x. So the f of x dx represent that I am adding f of xi delta x. So the notation is really try to reflect a little bit what this means. So we're adding f of x delta x. The a and b is the interval that we are interested in. Okay, so that's really where this notation coming from. Now, f of x, so in this notation, f of x dx, okay, f is called the integrand. We give it a name. F is called integrand. That's what we call the function f. A and b are called the upper and the lower limit of integration. So a, we called it the upper limit of integration. B is called the upper limit of integration. And a is called the lower limit of integration. Okay, so f is called the integrand. It means that's the function that I'm computing its left sum and its right sum. That's my f. It's called the integrand, the upper and the lower limit. Okay, so now we're going to do two things. First, we're going to estimate a definite integral, which is I did a minute ago, and then we're going to interpret the definite integral graphically, geometrically. What is geometric interpretation? So first question, because I've done it already, suppose we are told the following. So example number 1, before I interpret, no, actually let me interpret. Interpretation of the definite integral. Okay, graphical interpretation. It has lots of interpretation. So this is, we're going to call this graphical interpretation or geometry. I'm going to split my problem in two cases. Suppose f of x is positive on the interval AB. Okay, I'm going to split it in two cases because they are important. It means, suppose my function takes only positive value. So I am in this situation. Only positive. Then the definite integral. Remember, it's nothing more than the limit of those sums, of the left sums or the right sum. I'm taking right sum. But geometrically, graphically, what does this represent? Remember, when I'm taking, it's the limit of those sums, but those sums represent nothing more than the sum of the area of those. That's what the sum represent, because my function is positive. I don't really have any issue. So in this case, this represents the area, that's the interpretation, of the graph under the graph of f. That's what it represents for x between a and b. Because that's really the definition. The definition is nothing more than the sum of the area of the rectangle when we take a lot of rectangle. So I draw the picture again. So this is my f, a and b. Okay, the integral to the area of that, that's my area. So the area is what the definite integral represents when f is positive. Okay, that's the graphical interpretation. Now, what happens when f takes positive and negative value? Suppose f takes positive and negative value. Okay. What does the integral represent graphically? Again, the definition of the integral is the limit of those sums. But now when the function takes positive and negative value, what do those sums represent? And this is basically what we did at the beginning. Basically what we started at the beginning. So suppose my function here is going to take, this is my A, and this is my B. And suppose my function is like this. It takes positive, changes mind a little bit, then it changes its mind, and it's going to take negative value. So it's taking positive here, negative here, and then positive here. That's really my function. It's not positive anymore. It means this is my f of x. That's really what my f is. What does the integral represent? Remember, the integral is nothing more than those sum. I'm taking you back to the first picture. It's nothing more than what happened to those left sum when the number of subdivision becomes larger and larger. So graphically, what's really going to happen? When I take more and more subdivision, the sum is going to be the following. When the function is positive, I'm going to get the area under the graph, because the contribution of the sums will give me the area. When the function starts taking negative values, those terms, sum of those terms will not give me the area, will give me minus the area of this region. So what the definite integral will represent is the area of the region above the x-axis minus the area of the region below the x-axis. So when the function is negative, f times delta x is going to be negative number minus this area, minus this area, minus this area. And that's what really happened in the general case. So the integral is going to represent the following. When the function is positive, I'm going to call this, suppose the area here, I'm going to call it A1. This is f positive. This here, I'm going to call this area A2, that's the area. And this piece here, I'm going to call this area A3. Okay. Now, when I start taking those sums, when the function is positive, f of xi delta x represent the area. When the function is negative, f of xi delta x represent minus this area. Here, it represents plus this area. So the integral is going to be the following in this case. It's the area of the region. Area under the graph. Graph of the region. It's the area of the region above the x-axis minus the area I'm taking away the area under the graph below the x-axis. Means I take, so in the picture given, in our picture, the integral is, that's the interpretation, is A1 here, but it's positive. When it's becoming negative, that's minus A2. When it's positive again, plus A3. So it's the area of the region above the x-axis. You take away the area of the region below the x-axis, because the contribution of the Riemann sum now gives you minus the areas below the x-axis, not positive the area. So let me take immediately a quick example to elaborate this idea. So the definite integral is, if the function is positive, is the area. If the function starts changing, it's not exactly the area. It's positive, the area above the x-axis, minus the area below the x-axis. And the book is calling this the net area. The book called this plus the area above the x-axis minus the area below. The book is calling it net area. So very, very quick example, just to elaborate this concept a little bit. So suppose I give you the following function. I'm going to take a simple function, and I'm going to graph it. So suppose I have this function f. And I'm going to graph it like this. So I'm going to take that. So that's the graph of f. So that's my integrand. That's my function. So let me take this point. I'm going to call, for example, this is 1, 3. And then I'm going to take my function, kind of go down like that. And this is a 2. And let me pick a point here. I'm going to call this a 3 minus 4. And this is my function. And then it backs up like that. And this point, so that's a 4 in here. And let me call this point 5, 2. Okay, so this is my function f. So that's the graph, that's the function, that's the graph of the function. I'm going to ask only 3 questions. My questions are, first, evaluate each. Evaluate. Integral from 1 to 2 of f of x dx. So that's my function. I didn't give you a formula. We're just gonna give you the graph. And the question is evaluate using the graphical interpretation of the definite integral. My upper limit, actually let me put 0 here, make it easier. My lower limit is 0. My upper limit is 2. That's my lower and that's my upper. And that's my function. That's the f of x. So what the definite integral here represents is simple. Remember, it's really the reduced sum. But now we know that when the number of subdivisions become hard, the sum is going to represent nothing more than the area here. From here to here, my function is positive. So the integral is the area of the region A1. It's this area. So it's, let me call this D1 if you want. It's the area of D1, which is equal to, D1 is just a triangle. So it's half the base times the height, because this is a triangle. It means half, the base is 2, 3, which is equal to 3. That's from 0 to 2. All right, one more question. What's the integral from 2 to 4 of f of x dx? 2 to 4. This is my 2, and this is my 4. Okay? What does the integral equal to? And then I stop. Can anybody tell me what's the integral? First, let's search the function. F here is negative. So when I'm going to take those integrals, the integral is, remember, I will not, the definition is f of xi times delta x. But this time, every time I'm taking the f of xi times delta x, I'm getting minus the area. Minus the area, because my function is negative here. So this is going to be, if I call this d2, it's going to be minus the area of d2. So this is the integral is negative in this case, which is minus a half the base times the height. It means minus a half times 2, and my height here, okay, if I put my height is 4. So this is going to give me minus 4. Now, if I take the integral from 0 to 4 of f of x dx, what this is going to give me? From 0 to 4. My function now is positive from here to here, negative from here to here. So the definite integral is going to be positive this area minus the area. So here it's going to be area of d1 minus area of d2. Okay. Area of d1 is 3 minus 4, which is a negative 1. This area is larger than that, even though in the picture it doesn't show that much. Okay, so that's the geometric interpretation of the definite integral. It's not the area of the region, is what we call the net area, which means the area of the region above minus the area of the region below. Okay. All right, definitely I stop right there. I will give you homework, and this is really one of the, most important idea in this section, basically. And I'm going to put some homework on my lab. And if you have any questions, meet me in my office hours. Okay. Bye-bye, guys.